matrix A is minus 2, 1, 1, minus 2. When you solve the equation x prime equal to A times x, so we notice that this matrix is symmetric. So 1, 1 here. This is always diagonalizable. It has two eigenvalues. Minus 3 and minus 1. Lambda 1 minus 3, lambda 2 is minus 1. And correspond to that, we have v1, v2 eigenvectors. v1 is minus 1, 1. And v2 correspond to lambda 2, 1, 1. So you can practice to do this too. And now we use this to write out the solution of this differential equation. The eigenfunction f1t v1 e lambda 1t minus 1, 1 e minus 3t eigenfunction f2 v2 e lambda 2t 1, 1 e minus t, and the general solution. Say xt, so put arrows here, equal to c1 f1 plus c2 f2. c1 f1 plus c2 times f2. This is a general solution. c1, c2 here is a real number. So in case they give us an initial condition, say x at the point 0 is something, then you can solve for x c1, c2. Otherwise, we can stop right here. This is a general solution of this equation. Now let's draw the trajectory. So we have two axes correspond to the two components of these vectors, xt, x1 and x2. We have two eigenvectors, minus 1, 1 and 1, 1. Minus 1, 1. This gives us this eigenvectors 1, 1, minus 1, 1, and this is the eigenspace v1 minus 1, 1. It corresponds to c lambda 1 minus 3 negative e 3t e to the minus 3 3 tend to 0, t tend to infinity, so it would go inward equation. The second eigenvector is 1, 1. 1, 1. This gives us this eigenvectors 1, 1. We extend that, we get the eigenspace. v2 1, 1 correspond to eigenvalues lambda 1 minus 1. Negative e minus 1t tend to 0 when t tend to infinity. Again, this one will also go to the origin. For the other trajectory, what it does is as follows. The solution xt c1 times f1 plus c2 times f2. xt, the general solution, c1 v1 e lambda 1 t, c2 v2 e lambda 2 t. So in this case, we have lambda 1 minus 1, lambda 2 minus 3, lambda 1, so I put both lambda 1 here. Lambda 1 is minus 3, and lambda 2 is minus 1. Lambda 2 is minus 1. Lambda 2 minus 1. Lambda 1 less than lambda 2, but both of them are negative, less than 0. So therefore we have first along the two lines, let's go into the origin. Now we have for t tend to plus infinity. What happens is that this one is smaller, much smaller, e, so lambda 1 less than lambda 2, lambda 1 t less than lambda 2 t, still less than 0. E to the lambda 1 t would decay very, very fast compared to this one. It will be much smaller than E lambda 2t. A lot smaller. It will decay, it will tend to 0 so fast. This term disappear. What we see when t tends to infinity, there's only this term kind of left. So we can just follow v2 times something. So it's follow v2, the direction of v2. So it's solution xt will be parallel to vector v2 when t tends to infinity. So what we see is that v2 it should be something like that. It's parallel to v2 when t is big, parallel to v2 when t is big. Now let's look at the case where t tends to negative infinity. What happened? When t tends to negative infinity, this is negative. Lambda 1 less than lambda 2. Lambda 1 t will then be, so lambda is negative, t is negative, lambda 1 times t is positive, lambda 2 times t is also positive. And when you multiply a negative number, this inequality will change from less than to bigger than. So t, lambda 1t is bigger than lambda 2t is bigger than 0 because we multiply all of them by a negative number. And then you have e lambda 1t will then become so big compared to e lambda 2t. We tend to infinity. So what we see is that this term will be the one dominates. Sorry, e1t. So this one is dominates, e lambda 1t. So what you can see that it will be parallel to v1 when t tends to minus infinity. The solution xt will then parallel to v1 when t tends to negative infinity. So what we see is that when t is negative infinity, this is parallel to v1, the blue one, parallel to v1. So let's draw that. T tend to plus infinity is parallel to V2. Parallel to V2 flow. Right on when plus infinity. So what we see is that T tend to infinity is go to 0. Right? Parallel, so it go close to the direction of V2. Parallel to V2. You don't see that because it's go to infinity here. Right? T go to infinity. This one go along the direction of V2. Same in the other part. In this region, we have the same thing. Follow the direction of V2 when it's go to infinity. Follow the direction of V2 when it's go to infinity. Follow the direction of V2 when it's go to infinity. That's what happens when T is big. The curve will still go inward, the origin. When T is minus infinity, we have xt, the solution is parallel to V1. So out V is parallel to V1. So in this direction parallel to that, same the other side. Parallel to V1, parallel to V1, and parallel to V1. This go into the origin, parallel to V1. And then we just connect them. So like this. That gives us a few trajectory. Yeah, and the other trajectory to do the same thing. So we draw a few more. So first of all, let's talk about origin here. Everything go into the origin. This one will be a sink, a node. So we have the origin right here. The origin, in this case, this is a sink. Everything go into that is a node. This we say is a nodal sink. Yeah, just a node. And then now it's about a node. We can determine whether it's proper or improper. So in our case, this direction and this direction, opposite direction, but have tangent to the same line. So it is improper. Yeah. So it's an improper nodal sink. Yeah. So that is an example of the case where we have two negative eigenvalues and two distinct negative eigenvalues. We have the improper nodal sink.